So in this video, we're going to be working with the same place kicking data set, but I'm going to look at a different explanatory variable. More specifically, I'm going to look at a binary explanatory variable, or again, a categorical variable with two options. The variable we're going to look at is called the change variable. Now, we hadn't ever talked about this variable before because we hadn't used it in any of the examples that we've done. So a quick explanation of what change is. So since change is a binary variable, it's going to be coded as a 0 or a 1. What a 1 is going to represent is a lead change if the place kick is made, and 0 would be a non-lead change if the kick is made. Again, so what would that actually mean? So let's suppose that the team is currently, so we'll call it home and away. So if the home team currently has 33 points and the away team currently has 34 points, if the home team were to make their field goal, they would now have 36 points and would now be ahead when they were behind before. So when that happens, if that's the case, so if this kicker makes this kick, if they're now going to suddenly be ahead when they were behind, I'm going to call this change variable a 1. If that's not the case, then we're going to call that change equals 0. So when would that not be the case? Well, there could be a couple different ways that that's true. But suppose for a moment that the home team currently has 33 points and the away team has 50 points. If the home team makes their field goal, they will now have 36 points, but they're still going to be behind. So that would be a 0. There's not a lead change that would occur if the kick was made. Now, for those of you that are football fans, why this might be useful is maybe obvious, but for those that aren't, what this would maybe mean for the kicker is a little feel of a pressure effect. Because if they make this kick, if their team will now be ahead when they were behind, there might be an extra pressure put on them. Versus if they were already behind, they're still going to be behind, maybe there's less pressure. Or if they were already ahead, maybe there's less pressure. So this is going to sort of try to measure if there's a pressure effect, if there's a possible lead change in the variable. All right, so that's a very long, or actually probably a pretty quick football explanation of what this variable is actually going to mean for us. So in R, the only thing I changed here in the fit of my model is the actual variable that we used as the explanatory variable. Before we had distance there, and I've now just changed it to be the change variable. But now that I'm working with a different variable, I'm going to get different output. So here are now my new estimates that I'm going to get for my alpha hat and my beta hat. So now if I wanted to write out my estimated probability of success model, I still fit the logit link function, but now my alpha hat is 2.3149. I still have a negative beta hat, and we're still going to be multiplied by x. And then 1 plus the same thing on the bottom, just as before. Right, so the fact that it's negative, what does that tell me? So if it's negative, that would mean that when x equals 1, you have a smaller probability of success than when x equals 0. So that means that you have a lesser chance of making the kick if it could result in a lead change than if it doesn't. So that's that pressure effect, feeling like it might decrease their probability of success. Now, technically I fit a logistic regression model here, but I really didn't have to. What I really could have here is just a little two-way table. For my change variable, there are two options. There are non-lead change kicks, and there are lead change kicks. And then for my good variable, whether it was a successful or unsuccessful place kick, I could really get this little 2x2 table. And what this actually looks like from our data is there are 97 non-lead change kicks that were missed. There were 982 non-lead change kicks that were made. There were 68 possible lead change kicks that were missed, and there were 291 lead change kicks that were made. So I would already know how to calculate this odds ratio, right? I mean, that's something that we've done before, so that wouldn't be anything new here for me. So how would we calculate this odds ratio? And let me move this to the side here so we can do it. So again, I usually just do the cross multiplying, so I'm going to multiply those two numbers, the 97 times the 291, and then divide by multiplying of those two numbers. So 982 times our 68. Which would give us 0.4227. Okay, so just a little aside there. But now that I'm working with a binary variable, C will always be 1. So now if I want to find my estimated odds ratio, this theta 1, again, we're just going to take e to the beta hat. So in our example, that's going to be e to the negative 0.8611. Which is 0.4227. Look at that. It's the same thing. And of course, that's not a coincidence. So we get the same odds ratio, whether we calculate it from a 2x2 table here, as if we actually fit the logistic regression model. So we get the exact same odds ratio. But now what you can see is, so since this is less than 1, I'm probably going to want to actually invert this. But let's go ahead and do this here in R. All right, so fitting my new model here real quick, because I haven't already done that here in R. Oh, and I renamed my data set. So now if I look at my theta 1, there's that 0.4227. They just rounded it to 3 decimals. And so if I spit that out here, our estimated odds of a successful place kick are 0.4227 times as large for a lead change kick, because that was x equals 1, as for a non-lead change kick. So since it is less than 1, and I'm going to want to invert this, what is that going to change in our interpretation here? So when I invert it, what's going to change is the order of the lead change kick and the non-lead change kick, right? That's very what we saw before when we flipped it, is we now change the order of which thing is on top versus what's on the bottom. And so now our estimated odds of a successful place kick are a little bit more than 2 times as large for a non-lead change kick as for a lead change kick. And as this little note says here, since it's binary, you could do the odds ratio the old way, which is what we did here with just the little 2x2 table. All right, so new variable. Again, we inverted this odds ratio for easier interpretation since it was less than 1. Again, we actually did this. We verified the odds ratio calculation through our little 2x2 table. So does there seem to be a pressure effect? Maybe. And again, why I say maybe, even though my odds ratio was not 1, again, I really kind of feel like I need a confidence interval to truly answer that question instead of just an estimated value. The last thing I just want to do here is actually show, just as we did with the other one, how we got those values by hand. And so now when x was equal to our change variable instead of our distance, the first thing I want to make a note of, so since change is a binary variable that only can be 0 or 1, c will always be 1. Like, you're never going to see me try to plug in anything else for a c at all for a binary variable. So then to find our theta hat, again, we just took e to our beta hat, which was negative 0.8611, which gave us the 0.4227. But then we inverted it and gave us instead 2.3658. So a little bit different since I rounded the value. Right there, so there's some examples of the odds ratio interpretations for both a continuous variable for a couple of different values of c that you've seen now, and now we've also done it for a binary variable.